Natural radioactivity. You know, any unstable element or radioactive element decays to a stable element after a certain time. This process is called a spontaneous disintegration, or we can say spontaneous decay, as also we can say it's a nuclear decay or radioactive disintegration or a nuclear disintegration. You can say decay. In general, the unstable element decays to a stable element, or unstable element decays to a more stable element, because we can have a chain of decay, many chain or many sequences of decay from one unstable element to a new more stable element and new more and more stable element, and finally we get a stable element. So here in general we have a parent unstable element decays to a daughter stable nucleus. Okay, decay means we have a lose some quantity of energy by radiation. This radiation, it can be a particle emission, one particle emission, alpha, beta, beta plus, beta minus, neutrino, or it can be an electromagnetic radiation like gamma radiation. Anyway, we talk about each one in the next chapters. You know, we talked about this point before. In the case of a radioactive decay, or we get some kind of decay, occurs for all nuclei with Z greater than 82. And also you have some unstable isotopes with Z less than 82 or 83. Okay. In order to quantify the decay process, we have to find and measure many physical quantities. For example, we have to find the activity. Activity, it means we have to calculate the number of decays per second or number of disintegration per second. We have to find half time T half, the period where we calculate the time needed to reduce the number of unstable element to its to half of its initial value, and also we calculate lifetime tau is the time needed to reduce the initial value of the unstable element by a factor of 2.7 of its initial value. Anyway, I will talk about each one in details in the next slides. Okay, but in general, we have to calculate and measure, and you know the expressions of these parameters. Here we have a table where I show the reaction of each decay: alpha decay, beta decay, gamma decay, positron emission, and electron capture. Okay, we talk about these processes in the next chapter. First of all, we talk about the activity. We want to calculate the activity. The activity is the number of disintegration per second. Okay? It means here the activity of any element at a time t equals to lambda times nt, equals to minus dn divided by dt. We start with the definition of each one, of each term. You know, lambda, you have to know very well the definition of each one and the notation. First of all, lambda. Lambda is a decay rate or the probability of decay per unit time. What I mean, decay rate, it means, anyway, I will talk about this point later. We get some definition of lambda, the relation between lambda and n, and so on. In general, lambda is the decay rate and the probability of decay per unit time. Okay. N is the number of unstable element or the radioactive element at a time t. Be careful, I am talking about the unstable element only. Later, we can calculate the number of the stable element after the decay process. Equals to minus dn divided by dt. dn divided by dt is the number of disintegration per unit time. Okay, you know, the number of unstable, the changement of the number of the unstable element per unit time. In general, you know, dn divided by dt, the number of unstable element will reduce with the time. So the value dn divided by dt is negative. Okay, because the dn in general, you can say delta n equals to n final minus ln initial. Okay, you know, at a certain time, the number of unstable element will is reduced. In this case, the final number of n final is less than n initial. So delta n is negative. So the changement of the number of unstable element must be negative. This value is negative. We put here a negative value to get a positive value of activity. When we talk about the activity, it must be positive. So we have a negative here. So you have to know very well this relation. AT equals to lambda nt equals to minus dn divided by dt. The initial activity, this activity is at a time t. The initial activity equals to lambda times n0. Lambda is constant. N0 is the initial number of radioactive element and stable element at T initial. What about the unit or the units of activity A? Here we have two units. First of all, we have a becquerels BQ. 1 BQ equals to 1 decay per second. When we calculate A at a time t, which is equal to minus dn divided by dt, the unit of this one, or equals to lambda n t, the unit of A is decays per second. You can say here BQ, okay? Or you can have a unit Curie. 1 Curie equals to 3.7 times 10 power 10 BQ. Just a relation between BQ and CI and Curie. Maybe I give you the value of activity in Curie or in BQ. You can some exchange between these units. It depends the problem. Nuclear decay, or we can say decay's law. I want to find the expression of decay. It means how can we calculate the number of unstable element in terms of the time. I want to calculate n in function of time. How the evolution of the number of unstable element with the time. Okay, it changes with the time. First of all, we can start by the expression of the activity, you know dn divided by dt equals to minus lambda nt, or we have n lambda nt equals to minus dn divided by dt. Okay, so we can do the integration of each term here like this. You know, initially we have okay, here I put delta t here and n down. Okay, we get here delta n divided by n equals to minus lambda delta t. We do the integration, this term in function of n and this one in function of t. You know, initially we have n0 of n stable elements, and finally we get n at a time t from n0 to n, and that time it will be between t equal to 0, where at this time all the elements are unstable. Okay, we have an unstable element, and with that time the number of unstable element decreases and the number of stable element increases. Okay, we do the integration. You know, the integration of 1 dn over n equals to ln n divided by n0 equals to minus lambda t, where lambda is constant. Okay, you know exactly how you can do the integration. Finally, we get the radioactive decay law, where I calculate the number of unstable element nt equals to n0 exponential minus lambda t. You know, I repeat, nt is the number of the unstable element at any time, n0 is the initial number of unstable element, and lambda is the decay rate, and t is the time. Okay, we calculated before we have the activity. We can find a new expression of activity. Just here we can put t and t. We substitute the value of nt, so we get here lambda times nt equals to n0 exponential e lambda t. Okay, like this. Now we have two general expressions of the radioactive decay law, the number of the unstable element, and we have the activity A in function of time. Okay, the second properties, we have to find the lifetime tau. In general, lifetime tau equals to 1 over lambda. Okay, tau 1 over lambda. You have to know this relation. And you know A equals to lambda n, 1 over lambda equals to n divided by A. So here we get n over 1 over lambda equals to n over A. Okay, here we get n over A. Okay, no, it's the opposite. Let me see. Okay, here we have lambda equals to A over n. So we get finally, exactly, we get here tau equals to 1 over lambda equals to n over A. It's just a relation between the lifetime tau with respect to the number of unstable element and the activity. Okay. So Now the nuclear decay law, just we can write nt in terms of tau. nt equals to n0 exponential minus t times lambda. Lambda equals to 1 over tau. Okay, just I put here is the value of lambda. Okay, now we have this relation. At any time you can write it. Okay, nt in function of n0 exponential minus t divided by tau. And we said that tau is the time needed to reduce the number of the unstable element by a factor of e. What I mean? I mean at a time t equals to tau, n at time t must be equals to n0 divided by e. Okay, so we reduce by this factor. We have to arrive to this point. We must arrive to this result. Okay, we can say at time t equals to tau, we substitute the value of t by tau. Okay, n, we can write here n where t equals to tau equals to n0 exponential. Okay, we can write here we can say n at t equals to tau equals to n0 exponential minus tau divided by tau, so equals to n0 exponential minus 1 equals to n0 divided by e. So this is an important relation between nt and tau, nt and t, tau and a, tau and n. All these relations are very important to identify or to quantify any decay process. Okay, and you know E equals to 2.718.